Howdy there again. I want to start a new series of videos where we work through some problems out of basically a freshman and sophomore level physics textbook and approach these using Python and its numerical packages Numpy and Scipy. I have a whole stack of books over there from when I was an undergrad and also textbooks for when I was TAing undergraduate courses. So I have a variety of problems to choose from, and I might embellish some of them so that it's more amenable to using numerical methods, because a lot of these problems out of a textbook obviously are meant to be done by pen and paper and are a little on the easy side, but yeah, I think we can make this work. An issue I was having with some of the previous videos that I wanted to make is that I drew a lot of the physics and that type of thing from either my work or my PhD days, and a lot of that was pretty rather on the complicated side. I mean, even though I wrote some of the papers and wrote some of the articles and did the research, I didn't remember a lot of the details, and I had to go back and study it for like an hour or two just before beginning a video. So I figured it might be overkill for just basic videos on how to use Numpy, SciPy, and other numerical methods packages. So I'm hoping this series is a little more approachable. We're just going to work through freshman physics book. We're going to start off with motion in 1D, which is this video. Maybe do another problem also in 1D from the same chapter of the book, then move on to vectors, then move on to like forces and Newton's laws and whatnot, so we can get into more interesting problems that might require solving differential equations via the computer. So yeah, let's get started with a simple 1D motion problem. So this is going to be our problem statement, and I'm going to break it into two parts. One is just straight from the textbook, and the second part is just going to be an embellishment on that. So let's make this a little bit bigger. And let's see here. So here's the problem we're going to look at. We have the position of an object as a function of time here. So it's a cubic polynomial, and we're asked to solve for three things. What is the position at time equal to 1, 2, 3, 4 seconds? The second part is what is the object's displacement between t equals 0 and t equals 4? And then what is the average velocity of the object between t equals 2 and t equals 4 seconds? So not particularly interesting from a computational point of view. This obviously can be done with by hand. So this first part is obviously just going to be using Python as a calculator. Not particularly exciting or interesting. Even this part for this part B for this problem is going to be essentially the same thing. Python as a calculator because we have an equation. It's just plugging in numbers. The only slightly interesting part will be this one here, where we're going to pretend we don't know what the velocity is as a function of time, and so we're going to have to numerically somehow calculate the average velocity between t equals 2 and t equals 4 seconds. To make this a little more interesting, for part 2, what I did is randomly sample times and positions from that function here. So this is the data set we're going to have, and we're going to pretend that this is essentially data from a sensor. So we have a bunch of series of points, and we're asked to answer the same questions as in part 1 here, but we don't have a functional representation. All we have are a series of data points. So let's get started. So we're going to need Numpy. So we're going to import Numpy as NP. And let's put our functions in a separate cell. So we're going to define a function called position. That's going to take an argument time, and that's just going to return that polynomial that's given up here. So that's all that this function is going to do. So in a different cell, let's print out the positions. Let's answer part A. Again, this is Python as a calculator. It's not of any particular interest, but let's just do it anyways. So print. Let's just print I can spell position equals, and let's just call that position function at time equals to 1, and we'll copy this, we'll paste it in, this will be 2, this will be 3, and this will be 4. So let's run this cell. What did we do wrong here? Oh, I'm used to VI and not typing in this type of environment, so I did a replace here, and yes. So there we go. Yeah, I mean, it's a calculator, big deal. And before we move on to part B there, let's just put a comment in here. Come on. Just say part A. And we'll move down here and do part B. Again, this is just, again, as a calculator. So let's calculate that displacement. So let's print displacement equals, and this is between, if I recall correctly, t equals 0 and 4. So it's just position at time equal to 4. So let's just copy that. Minus position at time equal to 0. So displacement is equal to 12, which you would expect, because that function is 0 at time. This function here is 0 at time equals 0, so it's just equivalently the position at time equals to 4, which we already know at time equals 4 is 12. So yeah, there we go. Now for part C, we're going to pretend that we don't know what the derivative is. So before we need a way to numerically estimate the derivative, and before we move on, let us write a function that actually returns the exact derivative, since it's easy to calculate. So let's come back up here to this block, which I'm just going to use to hold all my functions, and we're going to define a function called exact derivative. It takes an argument t, and it's just going to return the derivative of that polynomial, which is just this. So we'll use this to compare against the exact our numerical estimation of the derivative. So let's calculate that, and let's write a function just called derivative. Derivative. Again, it's an argument t. And what this is going to do is just, we're going to take a small value epsilon, and that's going to be equal to 10 to the minus 6. This could be passed in maybe as an argument. It might vary from problem to problem. And let's see. And we're just going to use a central difference formula to estimate the derivative. So we're going to take our function position, evaluate it at t plus epsilon, and we're going to subtract off the function at the value of t minus epsilon and divide that by twice epsilon. So just an approximation of the derivative. And we can get away with this because we have a numerical function for the position, and we can evaluate this at time equals 0. This will be this term right here will be slightly negative, but that's fine. Fine for this. So yeah, we have an approximation for the derivative. So before moving on, let's just verify that this actually does what we think it does by plotting the actual exact derivative and then overlay on top of it this numerical approximation. So coming up here, I'm going to import matplotlib. .pyplot as plt, and I'm going to do this matplotlib inline, run that. Let's run that, and we'll plot this in a new cell here. So let's just do t is equal to np.linspace. Let's go from 0 to 5 seconds. And let's calculate the velocity, the exact velocity. So v underscore exact is equal to exact velocity. It takes t as an argument. And let's calculate, we'll just call it v, our numerical approximation. And we'll call that derivative, we'll use the function derivative, so der derivative. Again, that takes an argument t. And let's just run this to make sure we have no issues here. We do, and we have v exact equals exact velocity argument. Exact velocity is not defined, and that's probably because I called it exact derivative. Yes, I did. So this should be this should be derivative. Run that. Now what? Invalid syntax. What did I do? I deleted my parenthesis, didn't I? So there we go. Okay, so let's plot this. Let's go here, plt.plot. We will plot t comma the exact velocity, so v underscore exact, and we'll make this a black line. So let's go here, plt.plot t comma v, and we'll just do this as a blue dot. So let's see what this looks like. Oh, of course I screwed something up. What did I screw up? Did I spell exact wrong? I spelled exact wrong up here. Run. So yeah, there we go. Our numerical estimation of the derivative is pretty good to the actual values. So now that we have the velocity, we can calculate what the average velocity is. The question asks for the average velocity between 2 and 4 seconds. So we can calculate that via this formula here. So the average velocity is just going to be the integral of v as a function of t between our two times of interest, so 2 and 4 seconds here, divided by the difference between the two times, t2 and t1. In other words, the difference between 4 and 2. And then Numpy comes with a built-in function called trapz, which uses the trapezoid rule to do this estimation of an integral. So let's do that. Let's do that now. So in this cell here, we'll just put a comment, and this will be for part C. We'll define our time variable, so we're going to call it t sub int. That'll be the time over which we're integrating. What happened here? So let's do t sub int, and that'll be equal to np.lin space. We're going from 2 to 4 seconds. And let's calculate the velocity there. So that'll be our integration velocity range. So that'll be equal to the derivative on that time window there, t sub int. So let's print out average velocity equals, and we'll make a call to numpy.trapz. We will call, it takes the argument vint and then the corresponding x value, which is tint. And if you're familiar with the MATLAB versions of these functions, this is kind of the mirror image. In that case, if you're using MATLAB, this would be tint, comma, vint. And that's something I always get hung up on every time I switch between the two different platforms. And now we need to divide this by the difference in time. So it's 4 minus 2 is 2. So I'm just divided by 2.0. So let's see if I haven't made any typos, which, you know me, I probably have. Oh, I have not. And we get an answer of roughly 7 seconds and some error. So the exact answer is 7 seconds if you work this out by hand. So we're pretty damn good. Okay, so let's move on to part 2. And in part 2, we're going to use these data here. So what we're going to do is create this by sampling a bunch of random times between 0 seconds and 5 seconds, sorting them, so they're ordered, and then running them through this function here, this polynomial function. And we're going to get a bunch of data that might resemble something that comes out of a sensor system. So we're not going to have exact values at the times it asks for 2, 3, 4, and so on. We don't even have a time at 0, so we're going to have to figure out how to extrapolate out and do net displacement between 4 and 0. And then again, we're going to have to do an integral where we could do the trapz thing, but we have gaps in our data at some point, so it may not be the most accurate way to do it. So let's try to figure out a way to actually go about doing this. And let's go back down here, and I'm just going to put in this cell here, part 2, and we need to generate those data. And so how I did this was to use the np.random.seed command, and I set that equal to 1. That's just going to keep the random values the same for every time we run the cell. And then let's call a variable t-sampled, and that was equal to np.random.rand, and then I had 100 points, and this has to be between 0 and 5, and rand gives between 0 and 1, so I'm just going to multiply this by 5. And now t sampled is going to be equal to np.sort t sampled. Let's run this to make sure I didn't have any typos. It seems good. Okay. So let's do x sampled now. X sampled, and that's just going to be running t sampled through the position function. T sampled. And let's run that. Okay, that looks good. Let's just plot that quickly to make sure we're not that we're getting the same plot as above. So plt.plot t sampled, comma x sampled, and we'll make this a dot. Let's run it, and I did something wrong here. Plt.plot t sampled. There's an underscore missing here, isn't there? So yeah, that looks like the plot above, so we're good. Let's just remove this line for now and move on forward. Can I put that line back in? Yeah, I want to keep the plot for a while. So the way I want to do this interpolation and extrapolation is by using a cubic spline function. We could do a linear interpolation, but that's going to kind of give us, especially in this gappy area, it's going to give us like very trapezoidal things, which may not approximate the integrals or the derivatives very well. So we will use a cubic spline where we try to come up with a cubic polynomial that connects each of these points smoothly. And if you want a video specifically on cubic splines or splines in general, I can do that. They're not that difficult. Let me go back up here now. I want to keep all my imports together. So where do I have my imports? I want to put in that. So from the Scipy package.interpolate, we're just going to import the cubic spline function. So I need to rerun that so it pulls it in. And now we can go back down here and begin to build our spline. So let's put my cursor here, and I'm just going to make a comment here, create spline object, and I'm just going to call it CS for cubic spline, and we're just going to call the function cubic spline, and we're going to pass in t sampled and x sampled. So t sampled and x sampled. That should do it. So let's just run this to make sure. Yeah, okay, that works fine. So let's create a new t variable and plot what this function looks like. And let's show how this function works. So I'm just going to have t equals np.linspace 0, 5. And I'm just going to have, let's call it x int for x interpolated. In fact, let's make this t int just to kind of keep all the variable pairs together. So we have that x interpolated. So to get those interpolated values, we're just going to pass our time values that we want to have the function evaluated at into that function CS, into that object CS. So that should return, and that seems to run fine. That should return x estimated values at these interpolated, at the points that we're interested in the interpolation. So before moving on, let's just go down here and plot this. plt.plot x interp, oops, that should be t interp x interp, and let's just do it with a black line and run this. So you can see our spline is now a good approximation for the function. So yeah, let's keep it for now and move on. Let's go forward. So we want to do part A, which is the positions at 2, 3, and 4 seconds. So that's just a simple call to that interpolation object. So let's go down here, and we'll just write comment part A, and we will print position at t equals 2, and we will call, what did I do? Something looks funny. Oh, that is what I need. CS2. And that should do that. So we get a value of -2. So let's go back up here and see what we got for this. Where is it? -2 at oh, that was at 2 seconds. So did it want it at 1? Where did it want it? Oh, 1, 2, 3, and 4 seconds. So I did 2. So let's just copy this. Go in here, paste 1, 1. Let's paste and paste. This will be 3. This will be 3. And this will be 4. And this will be 4. Run it. Error. What did I do? What did I do? What did I do? Oh, no error. I'm sorry. So here we go. Let's see. We get an answer of 0, roughly, -2, roughly -1, and 12. Is that what we got up here? Where is it? 12 looks good, 0 looks good, 0 looks good, -2. Come on. So yeah, there we go. That's pretty straightforward. So let's move on to the next part, which is the displacement. I mean, that's going to be the same thing as this. So let's go down here, part B, and let's calculate the displacement. So print displacement is equal to, we're done with that string, so it's going to be at the position at 4, which is CS4 minus CS0. Now it's going to extrapolate out to get to that 0 point, and I'll talk about that in a bit. Let's just run that and see what we get. So we get a number close to 12, which again is what we'd expect. I have over here in this tab the documentation for the cubic spline interpolation routine, and you could set what happens when you're out of bounds. So you can set whether to extrapolate or not, and you have to be careful with this and then read through the documentation to figure out exactly how it's doing that. But because we're only extrapolating, if you look at our data, the lowest valued point is like 0.00005 or something, which is close to 0. So we're not doing a big extrapolation, so we can just get away with kind of being sloppy here. But definitely go through and look at the documentation if you're going to do anything outside of your data points, because things can go badly wrong pretty quickly. So let's go back to here and let's start to think about part C. So let's go up here, part C. And now the nice thing about using splines, or cubic splines in this case, is that we have between each data point, sets of data points, we have a cubic polynomial that represents that interpolation. So when we take derivatives, a derivative of a cubic is a quadratic, so we can preserve some of the shape that's natural to that curve. So this is convenient, and the fact that it's easy to differentiate a cubic polynomial, you can get an exact expression that's built into the Numpy code. So we could create an object called velocity, and we'll just call it CS, and that'll be equal to our cubic spline, and it comes with a function derivative, which will just return the derivative of that function. So then we can call VCS and get the velocity at any particular point. So now we can just solve the problem just as before. So we're going to print out our average velocity is equal to np dot trapz. So we're going to do a numerical integration, and we're going to call v underscore cs, and we're going to feed it. What do we want to feed it? Let's do np dot linspace, and we're going from 2 seconds to 4 seconds. So that's that. And then we're going to need to divide that by the time interval, which is 2.0 seconds. So if I've done that correctly, we should just be able to run this, and there's a syntax error somewhere, so I probably don't have some parentheses closed properly. Let's see, trapz. I need one more parenthesis here. So there we go, and our displacement is 12. Do we still have an error? Okay, we still have an error somewhere here. V underscore CS derivative. Oh, where's the issue now? Oh, linspace needs to be spelled correctly, so that's one issue. And I forgot to put in np.linspace 2, 4, our x values. So there we go. Down here, average velocity is 7, which we just got before. So yeah, that's it. Cool. So I ran a lot longer than I intended to, so I'm just going to call it quits now, and instead of doing a long outro, just say until next time. Take care. Bye bye.